Hello, this is Douglas Rumbaugh, and in this video I'd like to walk through a solution procedure that I've developed for tackling relatively simple programming problems of the sort you might encounter in an introductory programming course in early college or perhaps even high school. Now, this video actually accompanies an article on my website, which will be linked in the description. All of the source code listings are available there, as well as a text description of everything that I'm going to talk about here. So if you want to open that up and follow along, or if you prefer text or things like that, that's available to you over there. Link in the description. Now, as a basis for the example of this solution methodology, I'm going to use the problem which is currently displayed on the screen. This is an example or a homework exercise actually out of a programming textbook by Sedgwick, Wayne, and Dondero. It's titled Introduction to Programming in Python if you're interested. I'll also throw a link to that book in Amazon in the description. It's a fairly good, albeit non-standard approach to teaching programming using Python. In any event, the problem is as follows. In 1693, Samuel Pepys asked Isaac Newton which is more likely, getting 1 at least once when rolling a fair die 6 times, or getting 1 at least twice when rolling it 12 times. Compose a program that could have provided Newton with a quick answer. Now, this is a fairly simple programming problem, and especially someone who's a little bit experienced with programming could probably sit down and hammer this thing out off the top of their head in a couple of minutes, right? But if you're somebody who is not experienced with programming or who's just learning programming, a problem like this can provide a lot of difficulty because there's actually quite a bit here. There's a large amount of different types of programming constructs you're going to have to use, some kind of abstract representation of objects in the real world that you're going to have to use. So it's by no means a trivial problem, as simple as it may appear to somebody who really knows what they're doing already. Now, what I want to do is walk through a solution to this problem using a technique where what we're going to do is, rather than doing any pre-planning, we're just going to dive right in with the program in our text editor. We're going to take a look at this and we are going to render this problem in the simplest possible form. The first program that we write is going to be nowhere near a solution to this problem, but it will be a first step. And once we have the solution to the simplest possible variation of this problem we can think of done, we can gradually add complexity, gradually increase the scope of the problem, until at the end, we'll end up with a solution to the problem as stated. And actually, we're going to end up with a solution to not just this problem, but a variety of very similar problems, as you'll see. So the beginning step, the very first thing we have to do is look at this problem and establish what the simplest possible statement of this problem is, the simplest sub-problem we can think of. And the thing that sticks out to me is we need to write a program that deals with rolling dice. So let's write a program which rolls a single die 1 time and displays the result. That's it. So once we start with that, we can then add complexity and eventually get to the solution we're looking for. So we need to figure out how we are going to roll a die. And once again, this is the sort of problem which superficially seems very, very simple if you already know what you're doing, but if you've never seen it before, it could potentially pose some difficulties. So what I want to do is first mention how we might arrive at our solution to the simplest possible problem of rolling a die, because we somehow have to translate this idea of rolling a die into Python. Now, one good approach for tackling problems like this is to take the thing that you want to model, in this case a die, and start to list out all of the properties that you think that this object has, right? All the things that you may have to account for in your model, just everything you can think of off the top of your head. So if we're looking at a die, for example, tell you what, let's just call this, say die model.md. If we're thinking about a die off the top of our head, what are some properties that a die has? Well, it's a cube. It has 6 numbered sides. Go 1 through 6. You can roll it. And you can go on and on and on and come up with a whole bunch of other things. The numbers are often represented with dots. Often made of plastic. And on and on and on. You can come up with a big, long list of these things. And once you have that list together, what you should do is you should take this list and you should go to your the problem you're trying to solve. And you should compare the list to the problem. We'll leave that like that. And see if you can cross off the things that are irrelevant, right? So if this is the problem that we're trying to solve here, you can immediately see that there are going to be a lot of details of the die that aren't relevant to solving it. The fact that a die is made of plastic, potentially, or maybe bone or what have you, it's irrelevant. The numbers are represented with dots, also irrelevant. The fact that it's a cube is irrelevant, but what matters is basically this. And the die has basically 6 numbered sides, 1, 2, 3, 4, 5, 6. You can roll the die, and when you roll the die, there's going to be a face pointing upward containing either 1, 2, 3, 4, 5, or 6, right? One of those numbers. Equal probability of all of them because we're talking about a fair die, right? Fair die. That's what matters. So if we / cross through everything that doesn't matter, what we're going to end up with is basically that we need to come up with a model, a Python model for something that has 6 numbered sides that you can roll, right? Or to put it in slightly different terms, perhaps more Python-y terms, we need to write a Python program which is going to randomly generate a number between 1 and 6, right, the revealed face of the die, with each number being equally likely, and then display that. So let's go ahead and do that. I'm going to write a program called die.py that does just this. Now there's actually a number of different ways that we could approach the problem of randomly generating a random number between 1 and 6. I'm going to use the random.randint function here in order to do this. So random.randint has 2 input parameters, A and B, and those accept as arguments basically the bottom and the top of the range you want to generate. So if I wanted to generate a random number, 1, 2, 3, 4, 5, 6, one of those randomly, then what I would do is I would import random and I would call random.randint 1, 6, just like that. So that's going to give me that random number between 1 and 6. That's going to be the die roll, the face of the die when it rolls. And then I'm going to want to give that thing a name so I can reference it later. And for our simple case right now where we're just rolling the die 1 time, well, let's go ahead and display the result. So if I go ahead and run die.py, like so, you'll see I roll the die, I got a 3, I got a 3, I got a 6, I got a 6, I got a 3, got a 3, got a 1. How about some random number generation there? And that's the basic idea. We now have a program that will roll a die 1 time. Now, if we go back to our problem, that's not quite what we want. We want to roll the die 6 times and then also 12 times. Let's set the 12 time aside for the moment and just focus on 6. So we need to roll a die 6 times. Well, I kind of just did that, right? I could call this program 1, 2, 3, 4, 5, 6. There we go. There, I rolled the die 6 times right there. And that's all well, fine and good, but you do want your programs to be somewhat user-friendly. And there's no reason why the user has to be responsible for this. You could make the program do it automatically. So if this is the code to roll a die once, well, how do you roll it 6 times? Simplest, most straightforward approach is going to be just say, okay, well, if these 2 lines of code are for rolling a die once, well, if I wanted to roll it 6 times, let's create a program called roll 6.py. If I wanted to roll this die 6 times, well, all I have to do is go ahead and yank those. 1, 2, right? We can just paste this a whole bunch of times, 6 times. Since I'm using Vim, I'll just go ahead and do, oops, not that. There we go. A little bit of text editor magic, and we are good to go. So 1, 2, 3, 4, 5, 6. Sweet. We now have a program which will roll a die 6 times. Just like that. So every time I call this, you'll see we get 6 die rolls. Of course, this is by no means an ideal solution to the problem because it involves a lot of code duplication. We literally have the exact same line of code written here 6 different times. And it's generally a bad idea to repeat yourself when you're programming. So what we're going to do is, as our next step, we're still going to be tackling the same problem. I'm not adding another layer of complexity yet. We're just going to take this rolling multiple times thing and start to massage it into a better form, a prettier form, if you will. We can start by replacing all of this code duplication with a loop. So when you have the same code repeated multiple times, that's a good indication that this might be a place where you want to use a for loop, for example. So rather than copying these lines a whole bunch of times, what I can do is this. I'm going to say for something in range 6, this underscore, by the way, is just the Python convention for the name of a variable that you're not going to use. We're not using the number here anywhere in our code, so I'm just using the underscore. A more conventional standard boilerplate for loop would be something like for I in range 6. In this case, we're just using this instead. So for blank in range 6, this, which is going to repeat this code 6 times. Go ahead and run this. You can see, there we go. It does exactly the same thing. In fact, let me make sure that I actually saved it. It does exactly the same thing, but the program is a lot prettier. Now, while we are making tweaks to this, this 6 here is also somewhat offensive, if you will. You generally want to avoid what are called magic numbers. So we have the number 6 sitting in this code, but we're not really sure what it's for. So rather than just putting the number here, let's assign it to a variable and put that variable. So I could say roll count equals 6. And for I in range, roll count, like that. It does exactly the same thing. We just no longer have a random 6 floating around. Now you could extend that argument to the inputs to randint as well, right? That 1,6, but I'm not going to go that far. We'll leave those as is. You don't have to give a name to every single number, but some of them are a really good idea to do. And in fact, one of the reasons why it's a good idea to give this roll count a name instead of just putting the 6 is because why restrict ourselves to rolling the die 6 times when we don't need to? Obviously, our problem says we roll a die 6 times, but you may want to roll a die 3 times or 5 times or 100 times. And there's no good reason to prevent ourselves from doing that here. So what if we take roll 6 and we use that as the basis for another program called roll. And in roll, rather than having a fixed number of times that we roll the die, let's allow the user to specify. And we'll do that by using a command line argument. So I'm going to go ahead and import sys. And I'm going to make this equal to the first argument converted to an integer. So this is going to allow me, the user, to specify how many times I want to roll this dice, or roll this die. For example, if I call roll.py 6, I'll roll it 6 times. If I do roll.py 10, I'll roll it 10 times. I could roll it once if I want. it's always a good idea to try and generalize your program. This is now a generalized program because it doesn't roll at a specific number of times. I, the user, can specify how many times I want to roll the die. Generalization is always a good idea because it makes your programs more useful. And as a matter of fact, when we get to the end of this, we'll see how taking the time to generalize our specific little steps as we go through here is actually going to make life a lot easier when we get to the end of our problem. Okay, so that gets us now a program where we can roll the die as many times as we want. The next thing we're going to need to do is we're going to need to count up the number of ones. Right? If we go back to our problem statement here, and let me zoom this out so it fits better. We are looking at how likely it is to get the number 1 a certain number of times, right? Are you more likely to get 1 once rolling at 6 or 1 twice rolling at 12 times? So we have to figure out some way of figuring out how many ones that we have rolled. We have to count the number of ones. So let's make that our next complication. Now that we're rolling the die a bunch of times, let's actually count up the number of times that we get a 1. So we'll go ahead, copy roll.py, CP, we're on Linux, not Windows. We're going to go ahead and copy it, and let's call it count rolls.py. Like so, and we'll go from here. And notice what I'm doing here is what you should be doing if you're following through with this procedure is you want to save where you've been. You don't want to throw your code away, but you want to use where you've been as the starting point for your next step. The easiest way to do that is just to, when you finish and get a specific program working, just make a copy of it under a new name and then start editing the copy. And so that way we still have a log of, we have our die.py program here, we have roll 6, and we have roll. We still have all of our old code. If we wanted to roll back to it, if we needed to revert some changes we made, we can bounce back to an older file. We also have it around if we wanted to, say, go off in a different direction. It's a good idea to keep this stuff around. You should avoid deleting code as you go. In any event, we're now looking at count rolls. So we want to count the number of times that 1 appears. Not too difficult of a problem to do. We're going to have some counter. Let's call it 1 count. That counter is going to start at 0. And every time we get a 1, so if roll is 1, we're going to increase it. And see, because we're keeping the problem really simple, we're looking at just very simple, small problems here, the program practically writes itself. These are just individual little components that you're probably familiar with, even if you are a complete novice programmer. You know, how do you count things? Well, you start a counter at 0 and you increase it by 1. You can use an if statement to filter, right? We only want this to trigger if you have a roll of 1, so we'll just do that. Right, these are all, the problems are cast in simply enough that we're practically just working with the little individual programming components, nothing particularly large or heavy. We're keeping ourselves from doing a whole bunch of work at once, basically. So let's test this thing and make sure that it works. So count rolls.py, we'll roll a die 6 times, see how many ones we get. Oh. We forgot to do something. Which would help. It would help if we actually displayed the number of rolls, or the number of times that 1 came up, huh? Let's try that again. There we go. So the way this is working now is these are the rolls, right? These are coming from this print statement inside the loop, and then at the very end we have a print statement. That's the number of times that 1 showed up. So it will behoove you to run this a few times and make sure that it's actually working before you move on. All right, you want to, at each of these steps, you want to try and make sure that everything is still working okay. So let's go ahead and do this again. Still 0, still 0. There we go. So here we got 2 1s and we have a count of 2. So looking pretty good. Now at this point, we've pretty well confirmed that this is working. Probably a good idea to just get rid of that print statement now. We don't need it. The program is counting the number of rolls, so this is just clutter. It's useful for making sure it works, but once we know it works, it's okay to get rid of it. And so we can now run this a bunch of times, and there we go. We're getting a couple ones in our code. Now, you may also notice that we've just introduced another magic number, right? 1. So where does 1 come from? Well, 1 comes from our problem statement, right? We're looking for 1s, but there's no reason to restrict ourselves to that. So let's generalize this as well. So you could start by just defining a variable called, say, target, and setting it equal to 1, like that. Right, that's just gets rid of the quote-unquote magic number because it now has a name. It's called target. But we've already gone this far. Let's just make this a command line argument as well. Right, so now I can tell my program, roll a die as many times as I want and look for whatever number that I want. Do I want to figure out how many 6s I roll? Well, I just have to call this thing with a 6. And while we're at it, let's go ahead and take 1 count here and rename it to target count, because we're not actually concerned about specifically 1 anymore. So leaving it 1 count's not going to break the program, but it's probably a good idea to, what's the word I'm looking for? To rename it anyway, so it's not confusing. We're counting target, so we'll call it target count. And let's go ahead and just rearrange this so that all of our command line argument stuff is at the top. Probably also a safe bet. Okay, so now we can count, say, the number of 5s that show up. We're now counting 5s rather than 1s. This is not actually part of the problem we're trying to solve, but you may as well generalize it anyway because it doesn't cost anything and it might make this program more useful. Since we're doing this in individual little discrete steps rather than looking at the whole big picture, right? We don't necessarily know, because we don't actually have a plan. We don't know what generalizations are going to be important and what aren't. So your best bet is just to generalize everything as you go, within reason. Okay, so now we have a program which is going to actually count the number of times that a 1 shows up, or what have you, and however many rolls we want. The question, though, specifically doesn't want a raw count, it wants the probability. So remember that probability in this context is basically going to be the number of times that we run this program, the number of times we do this, and we get a hit on target, divided by the number of times that we ran it, right? So if I were to run this program 10 times, and I get at least a 1 on my output here, 8 of those 10 times, then my probability is going to be 8 divided by 10 is 0.8. Now, what this means is in order to calculate probabilities, we're actually going to have to take that highlighted code there and run it a whole bunch of times. We have to effectively average the result out across numerous runs in order for this to work. So we could just manually call count rolls a whole bunch of times like I did here and add it up manually. But again, like we saw at the very beginning, why bother with that when you can simply make the program do it for you? So go ahead and copy this into peppers.py. All right, new program based on the old one. We want to run this thing a bunch of times. How many times? I don't know. When you're calculating probabilities, the more times you do it, the better your answer is going to be. So let's pick a nice big number, say 100,000, and we'll do that. So we'll create a variable, assign a value of 100,000 to it, and then for blank and range test count. There we go. So we'll just run our code 100,000 times. Now I can run this. It is going to absolutely destroy my console here. There we go. So basically this is this program that went a lot faster than I thought it would. I guess it's pretty simple. This is the output of running basically my test count program, or my roll count program 100,000 times. So that's all you have to do to make Python do something 100,000 times, right? Is chuck it inside of a for loop. Now, while we're looking at this, these two guys here, the roll count and the target, are actually not going to ever change. Right, those are the arguments of the program. They're not going to change at all within that 100,000 rolls. So we may as well take those and move them outside. And let me just go ahead and do that. It's generally a good idea to put your command line argument stuff together at the top of your program. So we'll go ahead and do that. The program will still run just fine, right? Now, we need to actually figure out how we're going to get the probability out of this, because although we're running it enough times now, we have to actually make the calculation. So remember, when I define the probability, it's the number of times that we found our target divided by the number of tests that we run. Now, the number of tests that we run is this test count variable, so that's going to be the denominator of our probability, but we still need to figure out the number of times that we've hit target. The target's shown up in our roll at least one time. So in order to do this, again, it's going to be just a simple count, right? So I'm going to create a counter. Let's call it, what did I call it over here? Threshold met. So the number of times that we've met our minimum threshold for appearances of the target. So we'll start that guy at 0. Now I'm going to get rid of this print target count because we don't actually care about that anymore. What we do care about is if we found our target. So I'm going to take this code and I'm going to put it here. So this needs to be inside of this for loop, but not inside of the actual rolling of the die, right? Because we want to test to see if we've found a 1 in any of these rolls. So if at the end of rolling the die 6 times, or however many times we want, if target count is at least 1, then that means that we hit what we're looking for. So what I'm going to do is, after this, if target count, the number of times we found our target, is greater than or equal to 1, I'm going to take threshold met and increase it by 1. Just like that. So this is just counting up the number of times we've had at least one thing. And then when we're done, we can, of course, obtain our probability, which is nothing more than the number of times that we met the threshold divided by the number of tests that we ran. And we will print that, like so. So now, if I run my program, we'll roll 6 rolls, look for 1. There we go. The probability of finding a 1 at least one time in 6 die rolls is 0.66565-ish. It's not going to be an exact number because there's a random component, but it's going to be around that ballpark. And in fact, it turns out that's a pretty good approximation for the probability if you were to solve this thing out analytically. Now again, you may notice that in doing this, I've just introduced yet another magic number. 1. So let's go ahead and get rid of that magic number. I'm going to create a new variable called threshold. And in keeping with the pattern, I'm going to make this an argument as well, so I can specify whatever threshold I want. Again, we don't necessarily know at this point, because we haven't done any planning, which of these need to be dials and knobs we can turn and which of them are static. So I'm going to go ahead and make this a thing you can turn. It's easier to make it something you can turn and then not need to turn it, right, than it is to be stuck with something static and then suddenly need to be able to change it. So I'm going to make this a command line argument as well. And then replace this 1 with threshold, just like that. So now I'll run the program the same way with this. So this program is rolling a die 6 times and looking for 1, the number 1, to appear in those 6 rolls at least one time. You can see I get the same result. If I want to look for the number 1 appearing twice, that's going to require 1 to appear 2 times. And as you can see, the probability is substantially less. So there we go. Now you may also be asking, why is it that test count isn't an argument? Why didn't I make that something you can change? There's no reason not to. In this case, it's largely irrelevant. As long as you pick a big enough one, it's going to be okay. But you could make this an argument as well if you wanted to. In fact, all you would have to do, right, is this. And now when you call the program, you're going to have to specify that number as well. And you can then change the number of times you actually run the test. And what you'll find is that the bigger that number, the more consistent your results are, which I'm sure should make sense to you. I'll be doing another article and video specifically on this number here because this program is actually an example of something called a Monte Carlo simulation. And so we'll be taking a look at Monte Carlo simulations later. But you don't have to make this a dial if you don't want to, just because of the structure of the solution. It's not actually something that you need to be able to change as long as you make it big enough. So I'm going to go ahead and actually undo that change for simplicity. Okay, so there we go. So at this point, what we've done is we've gradually constructed this program, which is going to allow us to specify the number of roles we want per test, the number that we're looking for inside of those roles, and how many of those numbers we have to get. And it's going to count up the number of times that you get target numbers, threshold times in each set of roles. And actually, at this point, we're now done. Now, if we take a look at the problem that we started with, right, we're looking at rolling a fair die 6 times and getting one once, or 12 dies and getting 12 rolls and getting 1 twice. We've actually never even mentioned or thought about that 12, right? We have been specifically focusing just on this first bit, figuring out how many times we get 1 in 6 rolls, or how many times we get 1 once in 6 rolls. But because we've been going through and generalizing everything, right, setting up these as command line arguments and so on and so forth, we set up enough things as command line arguments that when we start to look at the second half of this problem, we're already done. Because, check this out. So this is the answer to the first part. What's the probability of getting a 1 to appear once in 6 rolls? It's that. If I want the second part, well, that's how many times do I get a 1 to appear twice in 12 rolls. That. And now we're done. That's the cool thing about generalizing as you go like this, is it can actually end up giving you the answer to problems you haven't started thinking about yet. So because we sufficiently generalized this program using these command line arguments, we were able to answer the question like that. And you'll note, if we look at the problem, the problem is very non-specific, right? A quick answer. Well, running it twice got the answer pretty quick. I'd be very surprised if this were a homework problem and this was the program you came up with, if your instructor would not give you credit for it because you didn't check both cases in the same run. I certainly would give full credit for this solution. In fact, I'd be far more impressed with this solution than with the other one because this is a much more generally useful program, right? So in any case, we're now done. We have just developed this program in a very gradual process. And that's one thing that I really want to sort of hammer home with this process here, is at pretty much every step, going from our very basic roll a die 1 time all the way down to here, we really weren't adding more than 1 or 2 lines of code each time. We added a for loop there, and the next time we would add an if statement and this and that. The individual steps were really quite small, to the point where hopefully they were fairly obvious what was going to happen. It was fairly obvious what the next step was going to be. And that's the real advantage with breaking a problem down into simple sub-problems like this, and then gradually increasing the level of complication, is it makes each individual step you take very small. And it's a lot easier to cross a distance of, say, 10 feet by taking 10 steps than it is to try and cross that same distance in one step, right? Especially if you're not particularly good at jumping. So in this case, by breaking it down into those really simple, small programs, we were able to gradually get our way there without having to address any big, complicated problems. So just to sort of briefly go back over the steps that we actually took, right? The first step was this die.py program, where all we did was we rolled a die one time. That's it. That was our starting point. Then we moved on to this program where we rolled a die 6 times. And remember that we didn't just jump right to this. Although you may be able to do that, but if you're not able to jump right to this, we didn't. We started by just taking die.py and repeating it 6 times. And then we took then we used a for loop, and then we used roll count. We got rid of the magic number and created a variable. And then we generalized it all the way by using a command line argument instead to allow us to tackle other cases, which, as it turned out, was quite useful because we needed to roll it 12 times 2 later. Well, not 12 times 2, not 24. We needed to roll it 12 times as well to solve the specific problem we were tackling. So this generalization turned out to be quite useful. And the next thing we did is we wrote a program that would do all this and count the number of times that 1 appeared. And then we generalized that. And that's what got us our, what did I call this thing? Count rolls. That's what got us this. And in this case, we also generalized the target we were looking for. Now, as it turns out, for the specific problem that we were looking at here, this was unnecessary. We didn't have to generalize this to get our answer. We could have just left this as a 1 because we never had to change it, right? To get our final answer to the problem, I never had to change the second argument away from a 1. So in one sense, this particular generalization was unnecessary. And it's entirely possible that had we sat down and planned out what we were going to do from the beginning, we may not have done that. And that would have been okay. But because we're not planning, we don't know what we have to generalize and what we don't. So we just went ahead and generalized it. It really wasn't that much effort, and it will potentially make this program more useful for addressing other kinds of problems like this, should the need arise. So that was our next step. And then we had to take this thing and do it a whole bunch of times. So we repeated this code 100,000 times, and then we started counting the number of times that we met our threshold, and then we generalized our threshold, and the result was our final solution right here, which is what we used to solve the problem. So the way that I have it split out, we actually took 8 steps to get here. We wrote 8 programs. I'm including the slight generalization tweaks to the individual ones. If we had done that copy and created a new file for each change we made, we would have had about 8 programs at the end of this. So we got there, little individual steps, and wound up with the solution to our problem. Now, this approach is laborious. We made a lot of different programs here to get to this one, and realistically, this one is the only one that we need. And it's definitely not suited for big problems. For a small one like this, it works out just fine, but if you're looking at really big, complicated problems, planning is useful. You know, there's that old saying that weeks of work can help avoid hours of planning. Planning is useful, but when you're looking at simple things and you're just learning, you don't necessarily know what to plan for, right? So it's much easier, I find, to just dive right in like this. So in this process, what we're doing is we're encouraging the examination of really specific cases. Right? Roll it 6 times. Roll it once. Hell, we started with rolling it once. And specific cases are a lot easier to get a handle on. They're a lot easier for particularly beginning programmers to understand. It's a lot easier to think about rolling a die 6 times than it is to think about writing a program that allows you to roll a die n times. Especially once you're good with programming, it doesn't feel like it'd be that big of a leap, but for a lot of people, it really is. So starting with specific cases and then generalizing them later can help alleviate a lot of pain with arriving at a solution like this. It also encourages you to think about really simple, small tasks, individual, minute steps that require very little effort to complete. And if you do enough of them in a row, then you actually wind up with your final solution. So it's this process of identify the simplest possible chunk that you can do, and then start gradually adding complexity to it. And that is a process that will serve you well throughout whatever level of complexity of programs that you're writing. And no matter how long you're programming, that's a very important ability to have. But in the early days, right here, it can really help with preventing you from feeling overwhelmed, which is a significant problem. You're not going to be able to just sit down and materialize a program out of thin air without a lot of practice. So this process is that practice. If you do this enough and you tackle enough fairly small, simple problems using an approach like this is what's going to train your brain to be able to think about the problems to the point where this process basically becomes automatic, and you can be one of those people who looks at that problem statement, sits down, and has this code hammered out in a couple of minutes, right? You can get there, but you got to do this first. It's laborious and it's a bit of a pain, but I found that it is the easiest way to do it in the early days. All right, so that is this process. I hope that you found this useful. This was kind of a lengthy video for what it was, but I do hope that this was useful to you and that you can apply this to programming problems that you're facing. It can take, even this takes a bit of practice to figure out, how to subdivide the problem, but you get practice by doing it. And it can really, really help save frustration and, believe it or not, time, I find, for people who are just beginning to learn how to program. So I hope that you found this useful, and I will see you again in the next one.